So before moving on to the empirical formula, what it is and why we need to first know how to do the percent composition. Yesterday we have learned actual yield, the theoretical yield, the percentage of yield. But still we need to learn some percent composition of each part element in the molecule or compound. Let's we will see here and why we need to do that. As I said that in the pharmaceutical company or food industry, we sometimes need to combine multiple chemical, vitamin or medicine. That time we need those type of percentage composition knowledge. It's very essential. As we know, this is just a repeat, the percent equal to parts divided by 100. That means if I say that, if we go to the any grocery shopping mall, we all obviously mostly see the 50% discount, 40% discount, 35% discount. That means 35 parts per 100. If we say the 10% discount, 10 parts per 100. And in case of chemistry, chemical, percent composition of a compound means the gram element divided by 100 gram of the compound. So since in other clothing we use like that parts, but in case of chemical we will be using gram. How, like if I say that 10% of this compound, that means 10 gram out of 100 gram, 10 gram element out of 100. So percent composition of a compound is the mass of element parts per 100 gram of substance. So let's see now example, it will be more clear. So how we can calculate? If the formula of a compound is known, a two-step process is used to calculate percent composition. First, we have to calculate the molar mass of the formula and then divide the total molar mass of each element in the formula by the molar mass and multiply by 100. How? Let's see. When we will see, it will be more interesting. Look into here. Calculate the percent composition of here H2S. We commonly say hydrogen sulfide or also hydrosulfuric acid. So if we look into here, so we have, let's see, we have this one. So now if I ask you that what is the percent composition? Percent composition means the hydrogen and sulfide. So in this compound, how many percentage of hydrogen and how many percentage of sulfur we have if we compare the total compound percentage? Yes, any question? Okay. So then first step, we have to calculate the molar mass of each element in a compound. So here H2S, so we know that how to calculate it. So the molar mass of two hydrogen atom is 2 and one sulfur is this 32.07. Second step, we have to find the percent of each element. So here, okay, I want to tell you something. Here is little bit of formatting problem. So the 34 you are watching here, this 34.07 actually the total mass. See, molar mass is 34.07. Okay, for the formatting it just come down and black one go up. So this is here. Okay, this is here, just below the below these two molar mass. So please, yeah, do not be confused. Now we have hydrogen 2 gram. So if we want to know the percent of hydrogen in this formula, so what we have to do in the second step, we have to have the amount in gram, molar mass of hydrogen divided by total mass. Total mass means the hydrogen mass and sulfur mass. Total mass is 34.07 and times 100%. So we will find this is 5.9%. Now let's do the percentage of sulfur. Similarly, we have the individual mass of sulfur divided by total mass of this compound times 100. Then we are getting 94.10%. Here I want to give you the nice, the little tricks that helps you. When you are going to calculate the percent composition of any compound, your calculation is going wrong or right, you can understand how these are so quantitative that if you now add these 2%, this 2% must be equal to 100. Okay, so even if you have a very big compound, like the 4 5 element, so you are making the percentage like that for each element. You are calculating the mass for the each element, and then you are calculating the mass percentage of each element in compared to the total mass of the compound. So let's see that this is not a 2, this is 5. So if you add or sum each and every percentage, eventually you have to get the 100. Okay, so this is the one trick that you can keep in mind, that your calculation is correct or not. Anyway, so let's move on. So this is how we have to calculate the percent composition. So how? We have two-step formula. First step, we have to calculate the molar mass of each element in the molecules or compound. So we will have the molar mass for each element, plus we will have the molar mass of compound. So then next step, percent calculation. For each element, the mass of that element on the top and down, we will put the total mass of the compound times 100. Then we will be getting the percentage of that particular element, and this is how you have to calculate the percent element of percent of each element in a compound. Let's see, here we have one biggest one. See, Ba3PO42. Okay, so Ba3. So first we have 3 barium atom here. Calculate the mass. We have, remember, when we have the parenthesis or bracket, just reminding that in that time we have to multiply each element with the parenthesis number, correct? So here we have PO4 parenthesis 2. That means we have 2 phosphorus here. Then 4 times 2 oxygen is 8 oxygen. So we have to calculate the mass of 8 oxygen. Then we will find the total molar mass 601.93. Please do not mind, when I will upload your presentation on the blackboard, your lecture, it will be okay, perfectly okay. But sometimes when we do PDF file or this type of platform, little bit of formatting change, and this is very common issue. So similarly, see, we find in this particular compound, the total molar mass barium phosphate is 601.93 gram. And now our job to find out the percent composition of each element. So the barium 411.99 gram, total 601.93 times 100, we find the 68.4%. Phosphorus 61.94 gram, total 601.93 barium phosphate times 100, we find the 10.3%. Lastly, oxygen, we have 8 oxygen, so 128.0 gram, 60 divided by 601.93 gram barium phosphate times 100%. So we are getting a 21.3. And I can assure you, if you now add this each percentage, you will get 100. Okay, so this is how we have to calculate the percent composition. Percent composition from experimental data. Sometimes they don't give you the directly. So in that case, what we can do that. So let's directly go back to the example, because example will tell you the same thing what we have here. Let's see the example. Chemical analysis of a sample gaseous compound show that it contained 0.54 gram of sulfur and 0.548 gram of oxygen. What is the percent composition of that compound? You know, what is the difference between two examples? First example, we saw that they show us the formula, correct? In the second example, they are not showing us the formula, but they are telling the uh, amount of each element. So you don't need to bother about that. Your job is to follow the same steps. Like you can see here, so in fact, you have to do little less job. How you have to do little less job? Because normally you need to calculate the mass, correct? But if you have this type of example, you don't need to calculate. Huh? You have to directly put the sulfur amount here, directly put the oxygen amount here, because you already have. So total, you have the total, whatever the compound, you have this amount. So you have to do, and you have to do the percent composition for the sulfur. Here we go. So 0.54 gram sulfur divided by total amount of and times 100. So 49.6%. For the oxygen, you have 0.548 gram oxygen divided by total mass of the compound times 100. You are getting the 50.4. And look at, if you now add these two percentages, these two equal to 100. So this is a kind of two types of percent composition that you guys normally need to do when we are considering to calculate the empirical formula and the molecular formula. Now we will be, okay, we have another example. So let's see. Here the same, we have nitrogen this amount, oxygen, total, you will do the same thing. So let's move on here. Do anybody remember about the empirical formula and molecular formula? I know some of you had last year or this year, last semester. Anybody remember what is the empirical formula and molecular formula? Okay, let's see what you do. Empirical formula is the relative formula. Relative in that case that we will get the whole ratio of the formula, like carbon, hydrogen, oxygen, that in the compound, how many carbon, how many hydrogen, and how many oxygen we have. But we are not getting the exact figure of the formula. That is it the ether, is it the alcohol, is it the carbon dioxide? We are not getting the exact thing. But we will get the how many carbon in the compound, how many oxygen, or how many hydrogen. That's why this is called the relative or empirical. This is, if we want to define it, so we can say the empirical formula is the simple formula expresses the smallest whole number ratio of the atoms present in a compound. The empirical formula gives the relative number of atoms of each present in the compound. As I said, that how many carbon your unknown compound have, whatever the information they are giving you, you can find out the ratio. That maybe I have 2 nitrogen, maybe I have 1 carbon, I have 3 oxygen, but you may have no clue for the final figure that what is the exact name of the compound. Got it? So what is the exact name of compound? For that, we have to know we have to wait till we figure it out the molecular formula. Okay? How to do the molecular formula. But before that, now we will be talking how to calculate the empirical formula. So I hope you guys got it. The difference between the empirical formula and the molecular formula. So empirical formula, you will get the compound name ratio, that how many each element you have in a compound. And this is the simplest whole number ratio of atoms. But in case of molecular formula is the true formula. True formula in that sense that we are getting the exact formula, what it is the compound. It is the ether, alcohol, which alcohol, ethyl alcohol, methyl alcohol. So we can find the exact name and formula of a compound. That's why the molecular formula is the correct or true formula of a molecular compound. The molecular formula represents the total number of atoms of each element present in one molecule of a compound. But over there, the empirical, we will get the ratio of whole number, but we cannot have the exact formula. So now let's see. We have some steps. So the first step, the atoms combine in a simple whole number ratio, the calculation of empirical formula. We know the whole number ratio that we just discussed. They are used to construct the empirical formula of a compound. Okay, let's move on. To calculate an empirical formula, we need to know the element that are compound, their atomic masses, and the actual masses of the element that are present or their percentage by mass. Now, if I now say these rules, it's kind of difficult. So let's go one example step by step and we can come back again here. Okay, let's see the example of empirical formula. The percentage composition of a compound is 34.60% aluminum, 61.54% oxygen, and 3.877% hydrogen. What is the empirical formula of that compound? So what is the ratio of aluminum, oxygen, and hydrogen? As I said, if the ratio is like 1:1:1, that means you have 1 aluminum, 1 oxygen, 1. If it has 2:1:1, that means 2 aluminum, 1 oxygen, 1 hydrogen. Now the thing how we can do that. We have some rule and this is fixed. We just have to follow and we need to remember the steps. First step, percentage to gram. You can also note it down. That's very easy. Percentage to gram. You know, if we go back to the rule, actually the same rule is here. Percentage to gram. So whatever the percentage we have, we will do like this type of table or just write on our notebook and in a gram. So if this is 34.60%, we will write 34.60 gram. If we have 61.54% oxygen, we will write 61.54 gram. We have 3.877 hydrogen, so 3.877 gram of hydrogen. Second step, convert gram of each element into mole. Now, we already know the atomic mass from the periodic table of each element, correct? And we know the atomic mass of each element per 1 mole in gram. So in that case, we have to look back into the periodic table. So first we have aluminum. See, aluminum is 26.9. So we have to, then we have the 34.6 gram. If we divide the original one, we will find that. Oxygen 16. If we just divide with the actually this is if you do the mass of conversion, you will find the same things. But here, now we know how to do that. So you can just divide with the actual mass, we will get the mole value. So that means first step, you have to convert from percent to gram. Second step, gram to mole. You know, in your presentation, you may also see the N number, both are same. Now the third step. What is the third step is interesting. Third step, you have to find which mole number is less. So because you know in the definition we saw the whole number ratio, correct? So that's why we have to find some whole number ratio. So that's why we have to find always when we convert percentage to gram and gram to mole, we need to choose the which mole number is low. Then we have to divide each mole by that number. Got it, everybody? So like here, take time here, because if you understand the rules, you done for whole chapter, correct? So take time. Here we have aluminum, oxygen and hydrogen. Aluminum 1.282 mole, oxygen 3.846 mole and hydrogen 3.877 mole. So which one is the lowest? Yes, aluminum is one. So next job, number 3, we have to divide each mole element by the lowest mole number. So let's do that. Here is step 3. See, change the moles of each element into whole number by dividing them by the smallest number of mole. So this is the step 3. So see, when we divide 1.282 by same number, 3.846 divided 1.282, and for hydrogen 1. So what we find? We find the aluminum 1 ratio, oxygen 3 and hydrogen 3. Now got it? So now we are close to done. The simplest ratio of aluminum, and this is the definition, that empirical formula is the relative formula and whole number ratio. Aluminum, oxygen and hydrogen ratio is 1:3:3. In that case, we can write the empirical formula like that. AlO3 and H3. But we are not sure that what is this compound? Is it the aluminum hydroxide, and what is this? Here we stop for the empirical. And if we need to make sure, we have to do 2 more steps that we do in the molecular formula. That's why empirical formula is the relative whole number ratio of a compound formula, and molecular formula we say the true formula, because by the knowledge of molecular formula we can calculate and find out the exact formula of a compound. Just think, it's interesting. You don't know. In the laboratory, they give you the some percentage of element, but you have your option to find out that what is exact number. So this is really crucial and useful in the not only the chemistry lab, in the science lab, in all part of science, as a pharmacy lab, molecular biology lab, chemistry lab, organic chemistry lab. Everywhere we always use this knowledge when we discover some new compound, when we isolate some new compound in the laboratory, either from the plant extract or from the other chemical. We always need to use this type of knowledge to figure it out which compound we have and how much. So I want to repeat once time. That might be helpful. Now let's go back to the rule. So if we want to do the empirical formula calculation, so first step, we have to convert the percent to gram. Now the question, if your problem directly have a gram, though you don't need to do the first step, correct? If you have if your amount in percentage, you just need to write percent to gram. If you already have gram, you don't need to worry about it. Even if you already have the mole, you also don't need to worry. Then you have to find the smallest mole number, and then you have to divide to find the whole number ratio. So same. Oh, and one more thing just I need to tell you. If you find like 2.9, 2.95, we can approximately round. Since our purpose to find the whole number ratio, so sometimes we saw that this is 2.9 or 2.95. So any question? Okay. So in that case, we can just round the approximate, okay? And also, you can see the decimal. Sometimes we find the decimal, like 0.5 or some 0.25. Normally we see the 0.5 or 0.3. So in that case, we have to do one more step like balancing of equation. So we have to just multiply with some number so that we can make it the whole number, because we cannot keep the point, so we cannot have the ratio of final compound. That's why. So what are the then rule? Final review to calculate the empirical formula, that when you will have a percentage of each element, you have to convert to gram. Second step, gram to mole. And third step, you have to find the smallest number of mole, and you have to divide each element mole by that smallest number so that you can get the whole number ratio. And then we will get our job done. So let's see the another example, because we will see some types of fraction here. Same, the percent composition of here nitrogen 25.94% and oxygen. What is the empirical formula of that compound? So we are going to do the same thing, percent to gram and gram to mole. And here, which one is the less? 1.852 is the less. That means nitrogen mole amount is less. So we are going to divide, use this smallest number to divide the each mole of nitrogen and oxygen for getting the whole number. And now let's see here, when we divide, we find that nitrogen is 1, but oxygen is 2.5. So when you will see that this type of fraction, your job to choose some number to multiply so that we can have the whole number ratio. In that case, I can see that if I multiply both by 2, then I can get it full number like 5 here, 2 here. So see, we did the same. So now our nitrogen and oxygen ratio is 2:5. So we can predict our empirical formula is like N2O5. Sometimes empirical formula also show you the last formula in the final, but this is very rare. If we want to get the final exact formula, we have to go through the molecular formula. So this is the another example, that if you have the fraction, how you should do that. Here is another example. 7.33 gram sample of lanthanum combined with 3 gram of oxygen to form an oxide. What is the empirical formula of the oxide? We will do the same. We already have gram, that I was talking that time. See, here we have gram, so we don't need to do the step 1. We will do the mole calculation, and then we will go to the choose the smallest mole number, divide each mole of element like lanthanum and oxygen. We will find the whole number ratio. And here, if you see, we find the 1 and 3.5 oxygen. So in that case, we also need to be multiply both with 2. Then you will find the 2:7. Got it? Yeah. Now let's see how we can calculate the molecular formula from empirical formula. As I said, even if your question doesn't ask you to calculate the empirical formula, your question may ask you the molecular formula. But in most cases, this is a process that first find the empirical formula and then the molecular formula. What we do sometimes, on the basis of points and time, sometimes we divide. How? Like we give you the empirical formula ratio and we ask you to do the molecular formula. In that case, your point is different. And if we ask you, if you need to do the empirical formula, and then obviously your point will be more on that problem. But you need to learn both. So let's see now. Now we know how to do the empirical formula, and now I'm repeating. This is how I do lecture, so that it goes into your brain at least. So again I'm repeating before going to the molecular, that for calculating the empirical formula we have 3 steps: percent to gram, gram to mole, mole to mole ratio. And in case of empirical formula, sorry, molecular formula, this is our rules. Molecular formula can be calculated. See, this is the rule. N equal to molar mass divided by mass of empirical formula. So that means ultimately you need the empirical formula for calculating the molecular formula. So the molecular formula will be equal either to the empirical formula or sum of n of it. As I said, sometimes molecular empirical formula is the final, but we have to go through actually to see that is it the exact formula or not. So here we have something. Here we have something, the formula. So you know, we cannot see here, but actually the molecular formula is finally the molecular formula equal to the empirical and n. So when we will find the n from here, we will get the molecular formula. This is, we have written here, I don't know why we cannot see, but we will go through again. We have example. Yeah, so this is the following steps that we need to do, but we will go for the example first. Yeah, that I was trying to say, right? See, molecular formula equal to empirical formula parenthesis n. So two steps. First, we need the empirical formula, and when we know the, we have to find the n, and n equal to number of mole, number of, I mean molecule, yeah, see, multiple of n, or how many n equal to 1, 2, 3, 4, 5, 6. So that n equal to molar mass divided by mass of empirical formula. So when we have these two, we will know the n equal to 1, 2, 3, 4, 5, whatever. And finally, we have the molecular formula equal to parenthesis empirical formula n. So if we have, for example, the empirical formula equal to CH2 and N we find equal to 9, that means the molecular formula will be CH2 9. That means C9 8 18. So now let's see how we could do that. What is the molecular formula of a compound which has an empirical formula CH2 and a molar mass of 126.2? As I said, that sometimes we give you that. In that case, because we make a question on empirical formula, we make a question on molecular formula. So sometimes we give that first do the empirical, then come, and if we have that time, your point will be higher. Like normally, like in other institute when I teach, and when we make this type of broad question, so you have to go down through the all empirical formula procedure and then this two-step molecular formula procedure. So obviously you will have a points like 6, 7, or 8 points. In that case, if you have to do the both all together. And if we have to do just either one part or this part, we put the 5 points or something like that. So your time and your hard work equal to OT, oath of exam points. So don't worry about it. So the compound, we have the empirical formula CH2 and the molar mass 126.2. So what we saw here, N equal to, let's go back again, molar mass divided by mass of empirical formula. So in that case, we already have the CH2 is a formula and the molar mass 126.2. So first empirical formula is already given, so you don't need to make it, we've done it. Second step, determine the empirical mass of CH2. We have 1 carbon, 2 hydrogen, find it 14 grams. So then we can calculate the N equal to molar mass. See, go back to the formula again. Molar mass divided by mass of empirical formula. So we find the molar mass 126.2. Most of the time it is given. Okay, most of the time molar mass given. If it is not given, then you have to again calculate. So mostly we give. So 126.2, and the empirical mass, whatever we have CH2, we find the 14. So so that means we find n equal to 126.2 divided by 14. So if we do, we have a n 9. We already have the empirical formula CH2. Now finally we know the molecular formula equal to parenthesis empirical formula and n. So this n should be this 9 equal to, and empirical formula CH2. So the CH2 bracket 9. So that means the exact true molecular formula for that compound is C9H18. Any question? Any question? Okay. So this is the thing, that if you need to calculate the molecular formula, first you need to do the empirical formula. If you have your empirical formula, it's very good. Then you have to find the empirical mass, and maybe you will have in your question the molar mass. So then you can calculate the n. When you will have a n, you can calculate the final molecular formula, that equal to parenthesis empirical formula and n. So when you put the n, you will find an empirical formula, you will find the true molecular formula. Let's see some example. Analysis of hydrocarbon. I don't know why it comes always. Okay. Analysis of a hydrocarbon shows it to be 94.1% oxygen, 5.9% hydrogen. Determine the molecular formula of the compound. If the molar mass of the compound is 34.02 and atomic weight they give you. Now maybe you got that you have to be done the gram and mole, and you have to gone through the process how to do the empirical formula. So if you do the mole and divided by the lowest, you find 1, 1. That means you very easily got the empirical formula OH. Now you guys have the molar mass 34.02. So 34.02, and the empirical mass you need to calculate oxygen 16 plus hydrogen 1, 17. So hopefully you will get your NC. So as I said that for 002, or if you see that it's coming 2.001, we can neglect those amounts, okay, smallest. Even if we find the 1.99295, we can round up like 2. That's how here we got 2. So now finally the molecular formula, empirical formula divided by n. So HO2. So that means it was actually hydrogen peroxide, H2O2. So for your final exam, if you review this presentation plus our current presentation, that's enough. You will be able to answer any kind of related math. So that was actually the how to do the empirical formula and calculate the empirical formula and molecular formula, and also you need to know how to calculate the percent composition. So we have learned all those here. Now we will go back to our lecture presentation, and I know most of we done. We will just review our presentation because we have time. So empirical formula, percent composition, I think same thing. Empirical formula from combustion reaction. Let's see. And then this is from the yesterday. So yeah, practice yesterday. So stoichiometry. Imagine that you have an unknown hydrocarbon, a compound that contains only carbon and hydrogen. Experimentally, you determine that compound contains this amount of carbon and this amount of hydrogen. So, you can calculate the mole and the ratio. Now you saw why I show my presentation first, because my presentation giving you step-by-step instruction how you have to do that. That's why now we will be review and it looks so easy now. So yeah, so that's the thing, that if we have the gram, we can convert into mole, and from mole we can find the ratio. But yeah, they will tell. This is just the beginning slide. So the mole ratio formula is here. We have to do the some whole number, so they did like that. So the chemical formula is made up of only whole numbers, C, the two, so C2H3. This is our empirical formula. Empirical formula does not represent the actual molecule. It is just a representation of the smallest whole number. That same thing we learn. So now then, empirical formula and molecular formula. Empirical formula based only on the mole ratio, and based on the mole ratio and total molar mass. Empirical and molecular formula: benzene, sulfur, this is glucose. So the ratio here, carbon and hydrogen, 6,6, that means 1,1 CH. Sulfur S8, 8,1 sulfur. They show the ratio here. So molecular formula and empirical formula. Empirical formula, we have the ratio, but we don't know the exact. So we can find when we go through the step by step. Empirical formula: simplest whole number mole ratio of atoms within a molecule. So gram to mole, mole to empirical formula. So I hope that now the way we have our presentation, it will make you very easy here, correct? Because the presentation gives you very straightforward rules, so that will not give you any chance to confuse. My suggestion to you, that I'm going to post the presentation right now after the lecture. My suggestion that when you will review, do that presentation slide and practice here all the problem. Got it? That will be more easier for you guys. Determine the molecular formula of cadmium if it has a molar mass of 204 gram and the empirical formula. So I think from the question you got it, that this is your molecular formula question. Second one. So you have your C5H8, they give you here, and you have the molar mass. So first, actually, you have to calculate the N. For N calculation, you already have 204, and then you have to find C5 and H8. So I think 68, almost 68 or something. So you will find the N number, and you have the C5H8. So if you do here, okay, let's do here. They don't have the exactly the same. So see, can anybody multiply 204 divided by 68? 3, huh? Okay, if it is 3, that means our next job will be coming C5 H8N. That means, the molecular formula equal to empirical formula and N. So C5H8 and 3. That means if we write here, let's do the overwriting here 3. So C15 and H24, correct? Yeah, H24. So this one. So I think that way we learn, it's more easier. It's more neat and clean stepwise. So there is no chance to become confused and no chance to become worried. Determine the molecular formula of cadenophyte. We did this one. Yeah, this is here now they did. But I think we already have, we just need to practice here. Correct? And if we look back how they do, actually the system is same. Molecular weight of the compound is 24 gram per mole. Molar mass, the same thing that we did, 68.11. So this is the N. This formula, this is actually N. N equal to, they did. Okay. So then we find the molecular formula equal to C5H83, this one. Got it? Yeah. So when you guys will practice, maybe you don't need to write all about step by, writing sentence wise, but if you just do the step 1, step 2, step 3, that will be never forgetting things. Percent composition. We know now how to do the percent composition, correct? The empirical formula is C3H5O2. CXOHYOZ. So XC, YH, and JO. So gram carbon, gram hydrogen, and oxygen. So what they did 100 minus, they add this is, and they find the oxygen. But actually this is the same thing that also we can do that, the percent composition first and then the empirical formula. So I will suggest you follow. I don't want to give you the two things that can be, but this is actually the same thing that we did. So you guys can look into here. So obviously, if you have the two element mass, if your compound have 3 elements, if you subtract the 2 from 3, 2 from 100, then you will find the mass of the third one. That's they are telling here. And also, you can gram to mole, and mole to you can find. And when you will have a fraction, you must have to multiply with some number to make it the whole ratio. Correct? They are telling the same thing, but maybe way a little bit of different. Let's consider this one. Yeah, so do the percent to gram, gram to mole, mole to ratio. The composition of adipic acid is this percent, this percent, this percent by mass. The molar mass of the compound is, what is the empirical formula? Okay, so you have to do percent to gram first. Gram to mole and mole to mole ratio. So if you do that, you will find it. Percent composition, gram, mole, simplest empirical formula. Okay. The composition of adipic acid. Okay, so this is just do. Please practice here. Empirical formula, simplest whole number mole ratio of atoms within a molecule. Yeah, we done it. And after empirical formula, we know that what we have to do. So we have to find the N. For that, we will have 1 molar mass, and we have to find the empirical mass. When we will have the empirical mass, we can do the molecular formula equal to empirical formula times N. So you will find here N, and then you will find it. That's the same thing they are telling. If we have 100 gram of butane, how many grams are carbon and how many grams are hydrogen? So we have total carbon before reaction. So they follow the same chart that we did in the last class. You remember the limiting reagent? They use the same thing is here. Let's do that here, these examples. So we have 100 gram of butane. So here, before reaction, 100, and do you know what they find here? This is the butane molar mass per mole. You know, they calculate here for 4 carbon and 8 10. So when they divide it, they convert the gram to mole. So when they have gram to mole, so we have 1.72 mole of butane. And from the balance reaction, we know that we have 4 mole carbon and 10 mole hydrogen. Got it? So that's why they compare the ratio here and the existing ratio before we start the chemical reaction and the mole ratio from the balancing of reaction of carbon and butane. This is 4:1, correct? So that's why they find that after when the reaction happen, they find the 6.9 mole carbon, and similarly they find the 17.2 mole hydrogen. Now after the reaction, they again convert here the mole to gram. Again convert their mole to gram, and finally they tell that how many grams of carbon you have here. Got it? In this particular example. So if you have this type of question, I want to review one times. I need to review because your final question comes from the arts. So it is my job to give you every explanation, and it is recorded. So you will also have enough time for final exam preparations. So please utilize that. I know that you all want to go to the next semester. So take it few days seriously. You will be able to go to the next semester. So if you have this type of questions, that like here you can see the balancing of chemical reaction and they give you the 100 gram of starting material. So how you can do that? Because we know the molar mass per mole. So we can convert the gram to mole of the starting material. So when we have the mole information of starting material, we can find the mole of each product by comparing their mole. So we need to find out the mole of carbon. So carbon and butane ratio here is 4:1. So that's why we always know the conversion factor, that which unit we have to find out, we have to write on the top. So since we have to find out the mole of carbon, that's why we write the carbon ratio 4 is top and the butane ratio C4H10 ratio 1 in the down. This is how we go, and times with the total mole of the butane, and we find the carbon mole. Similarly, we find the hydrogen mole. So when we have a mole, we can convert from mole to gram, because we know in case of carbon 12 gram per 1 mole. So obviously we can have the information in gram for the 6.9 mole, correct? It's a kind of normal multiplication, that if 12 gram for 1 mole, or 1 mole equal to 12 grams, so 6.9 mole equal to 12 times 6.9, correct? Same things is actually, but follow your rules, it will not make you confused. Similarly, we convert the hydrogen product mole into gram, because why we are doing, because we ask you in a gram, that's why. If we ask you in a mole, we could stop here, correct? But since they ask you gram, that's why here. So then finally we find the gram of carbon, gram of hydrogen, and total gram of starting material, that was. And also I can tell something directly. I think you will get it. Can you just do the C4H10, how many it comes? It comes the 58.12 gram, correct? I see. 4 carbon 40. I see. Okay, just a minute. So this is comes 48, 58.12, 58.12 grams. This one, and 4 carbon comes 48, and 10 hydrogen comes 10. This is the one tricks I'm giving you. This is unofficial tricks. So even if you just calculate in gram, you remember you can get the ratio. But for the final 100, you have to round up for the 100. Got it here? But actually the thing is the same. So 58.12, 48 plus 10. So 48 plus 10.12 because hydrogen 1.0 something, correct? So actually you are getting the same information here in the beginning without doing all those things. Got it? Yep. So here we have the same thing. We know how to calculate the percentage. When you will have a gram, you know how to calculate the percentage. Don't be confused because, correct? So if you have a percentage or gram of each element, you can just sum all the elements and the individual mass divided by total mass times 100 is percentage. Same thing is here, just to make sure. Percent composition from the formula. In that case, if you have only formula and ask you for the percent composition, first same, you have to find the mass for whole and then you have to find the individual mass and then the composition percent, okay? Yeah. The percent by mass of sodium in sodium sulfate. So same thing, you have to first write the sodium sulfate. Then you have to find the in a gram. So it will be total gram, correct? Total gram you will find here, and then you have to find the sodium amount. So when you will have the sodium amount, you have to do the sodium amount on the top, total mass down, and times 100. You will find it. Yeah, so sodium 22.99 gram here, because here you have the 2 sodium, correct, atom? And total sodium sulfate, we have 142, look into here. So then 2 times 22.2 divided by 140 times 100. Same formula. Obviously, same calculation will be same formula. But remember, when you calculate the molar mass of any element or compound and use your periodic table, do not forget that you need to use mass, not the atomic number. Because I have seen many students miss it because they have a tension in an exam, and when they look into the periodic table, they often use mistakenly the atomic number than the atomic mass. Remember, for this type of all calculations, we need to use the atomic mass. That means proton plus neutron number, not the proton number. Let's see the combustion of compound. This is how actually you do. We all do who use the motor vehicle. You know that nowadays most of the motor vehicle used by gas, huh? And I think now price is very high. Yeah. Sorry. So let's see what we have. Combustion of a compound. So this hydrocarbon, oxygen, carbon dioxide plus water. Ammonia plus oxygen, nitrous oxide plus water. This some example of combustion reaction. So CXHY means mostly the hydrocarbon, NY means the ammonia, and here CXHYNZOA, this is for this reaction. So this is for the green reaction, orange, blue, and iron. So these are the product. Okay, let's see. Combustion of a hydrocarbon, CXHY plus oxygen. If you combust 1.59 gram of hydrocarbon and collect 5.11 gram of carbon dioxide and 1.74 gram of water, what is the empirical formula? Okay, so in that case, first we have to know here, and then we can do the same thing, percent to gram and mole. So let's see what they do here. From 5.11 carbon dioxide, find 1.39 gram carbon in original sample. From 1.74 gram water, find 0.19 gram H in original sample. Converting to mole and empirical formula. So actually the thing is that we have to find the gram. So the way is the same. Individual weight divided by total times, you will find the gram of initially. All the carbon dioxide comes from the hydrocarbon. All the hydrogen water comes from the hydrocarbon. If we can find the gram carbon in carbon dioxide and gram hydrogen in water, we can effectively determine the composition. So you have here, see the same, the individual per mole and what we have total here, and we have the existing amount. So we will find the gram carbon and hydrogen. So follow it and then do the same. So sorry. So the gram to mole to ratio. So I will suggest you that please review some this maths problem, learn from the presentation that I do, and just practice it. And this is the same things, you have to do it. This is also combustion, yeah, and that's all. More practice. Actually, this enough for your final exam. From here, you will have the similar. Maybe little bit of I can just say that maybe little bit of I will change. So how I will change? So I want to show here that what type of change you may expect. Like 0.983 gram sample. So maybe here you may change little bit, maybe here, or reaction little bit. Otherwise, you will have so many example. I know that your final exam will be 18 chapter, but final question will come from already department. You have an idea of what you are going to see. But I know that they are not going to give anything that's not from our syllabus. So hopefully it will fine. So that was the all for empirical formula or molecular formula. So is it tough? No. It's a step by step. You have to practice, and whatever the practice your presentation slide has, little do it, you will know. Any question? Feel free to ask me. Now we will be doing our recitation. Yes.